the first shifting theorem says that there's this relationship between multiplication by an exponential in time space and shifting in S space. Now, we want to know if the converse is also true. Does a shift in time space give you multiplication by exponential in S space? And the answer is almost. Now, in order to try to show that to you, we need to talk about the unit step function. Now, remember that the unit step function is a light switch. It essentially says it's off until time A, at which point it discontinuously jumps and turns on at time A. And so, we're going to consider the following combination. We're not just going to talk about a function that's been shifted in time space. We're also going to then multiply it by a unit step. And according to the definition of Laplace transform, this is going to be e to the minus st, f of t minus a, u into t minus a. Now remember, unit step is nothing more than just turning something off and on. And because the unit step turns on at time a, all this is going to do is change the limit of integration to a, and that function, the unit step symbol, will disappear and essentially just be replaced with a 1. Then what we can do is play a substitution game. We'll say u is t minus a, du is dt. When t is a, that's going to give us u is 0. And when t goes to infinity, u will still go to infinity. So we'll end up getting a new integral that looks like this: 0 to infinity, e to the minus s plus a. So if we do that reorganization, and sorry, it should be s into u plus a. My apologies there. F of u du. That can be split apart: 0 to infinity, e to the minus sa, e to the minus su, f of u du. Here, u is our dummy variable. This term has nothing with a u, so we'll get e to the minus sa, integral 0 to infinity, e to the minus su, f of u du. This u is really a dummy variable. So if I felt like it, I could use any other dummy variable I want. And I'm going to choose t again. Now, it's not the same t as it was before, but it doesn't really matter. It's a dummy variable. So what ends up happening is I get e to the minus sa, and this is the Laplace transform of my function f. So I end up with the following result: that if I take the Laplace transform not just of a shift in t space, but a shift that's been weighted by a light switch, a unit step function, this ends up being multiplication by an exponential times my transformed function. So that's almost an analogous result. So this is what we call the second shift theorem. That if you multiply a shift in t space and you weight it by a unit step, it will give you an exponential in the other space. Now, conversely, if you want to switcheroo and apply the inverse Laplace transform of an exponential function of a function weighted by an exponential is going to undo just to give you that shift weighted by the unit step. When working with this, I think it's really useful for you to think of it like so. It'll be the Laplace transform of this function, and then you're going to shift the whole thing into t minus a and weight it by a unit step of t minus a. This is one of the tools that allows us to work with DEs that have discontinuous functions. And here's an example of that. So let's say we have y double prime for y is f of t, y of 0 is 0, y prime of 0 is 1, and our function f of t is going to look like this. It'll be a light switch, but a different flavor of it. It'll be on for effectively 1 second, and then it will be off otherwise. So really, really important skill here when working with unit step functions in Laplace transforms is, how do I write this in terms of a unit step? Because my goal here is to put this in terms of a unit step so that I can use the translation theorems, right? The picture kind of works like this. It'll be a 1, it'll be on until that first second, and then it will be off. So you might need to pause and take a little step here, but what you can think of is say, look, I want this function to be on. I want it to be 1, and then the light switch kicks in, and it turns off. And so I'll get 1 into the following. So it'll be U1 subtract the unit step at t minus 1. Remember, the unit step turns on at time 1. That's why that dot is filled down here at the bottom. And now we can tackle this differential equation if we think of this side in terms of the unit step. So I'm going to apply the Laplace transform to both sides. And now the shifting theorems are going to kick in. So I'll walk you through this. We've already talked about something similar to this left-hand side, but we'll walk through it again. Remember that we're just calling the transformed version of y of t, we're going to call it capital Y of s. That's the convention we use. We like to use capital letters for the frequency space results. We've already talked about this. This is going to give me an s squared capital Y of s. And this is where the initial conditions come in. We'll have s times y of 0 minus y prime of 0. If you have all rest conditions, all of those terms go away, but we don't have all rest conditions in this particular problem. In this particular problem, what we've got is a 1. And so because of that, this is going to kick in and give us the following result. We'll have a negative 1 here because of that initial condition. And over on the other side, what we're going to need to do is simply apply the Laplace transform, apply the linearity. This is going to give me 1 over s. You may or may not remember that the Laplace transform of a unit step essentially just has that exponential function that has a weighting according to where the unit step turns on. So all of this is a little bit of a mess. We'll have s squared plus 4 into capital Y of s minus 1 is 1 minus e to the negative s over all over s. When the initial conditions are non-zero, this is going to contribute another term. And so what we'll end up with is the following. We'll have all those terms we had before, but everybody is going to get divided through by this 1 over s squared plus 4. And that is the solution to the algebraic version of our differential equation, except that exists in frequency space. But we didn't start this problem in frequency space. We are starting this problem in time domain. So what we need is to invert this Laplace transform. And that means we need to take the inverse of this entire expression. Now, there are 3 terms that we're going to have to deal with here. And again, linearity is nice when we've got a function here and it's a sum of terms. What we can do is split this up by linearity. Some of these transforms are easy. Other ones will require a little more work. Now note that we haven't used any of our shifting theorems yet. This is going to start kicking in just a moment. And I'm going to do these in order here. I'm going to do them in order they appear. We'll talk about this expression first. So the inverse Laplace transform of this is very straightforward. This is going to give me a 1/2. I'm going to put a 2 up top. And this will be 1/2 times the sine of 2t. So that term is easy. The second term requires a little more work. here we're going to need to use partial fractions. And so the idea here is that 1 over s into s squared plus 4 is a over s plus bs plus c into this term. The whole idea is that if both of these terms have the same denominator, then their numerators have to be the same. So we're going to use these test values. And in particular, we'll say when s is 0, well, when s is 0, we'll have 1 into 4 times a plus 0, so a will have to be a quarter. And the other test value is going to be designed to turn the other factor into 0. Well, this factor is going to get turned into 0 when s is 2i. So we'll have 1 is a negative 4 plus 4 plus, and now we'll get 2bi plus c into another 2i. So 1 plus 0i is on the left is going to give me the following. I'll have negative 4b plus 2ci. We have to equate real parts and we have to equate imaginary parts. So the real parts over here tell me that 1 is equal to negative 4b, so b has to be negative 1/4, and 0 has to be 2c. And that tells me that c has to be 0. So the partial fraction decomposition here says, look, this expression that I had before really can be expressed as follows. It can be 1/4, 1 over s, minus 1/4 s over s squared plus 4. So if you kind of scroll back up here, we found that a is 1/4, b is negative 1/4, and c was 0. So that term just vanished. Linearity kicks in. We'll have 1/4 Laplace transform of 1 over s, subtract another quarter s over s squared plus 4. Both of these transforms are straightforward to get. We'll get 1/4 times 1 minus 1/4 cosine of 2t. Now that's important. We're going to need this term. And the reason we're going to need this term is because it effectively appears again in this third expression. So if you compare 2 and 3, all that differs between them is that exponential. And that exponential is where the shifting theorem is going to kick in now. So just to bring this up, the third term says we need exponential e to the minus s 1 over s into s squared plus 4. Okay, so the second shift theorem, here's what it says. It says if you need to take the inverse Laplace transform of e to the negative as times some function, you are allowed to think of this as f of t minus a times unit step of t minus a, which really the calculational way, or the probably the most useful way of thinking of this, is to say the following. I'm going to have a unit step of t minus a, in this case, times the inverse Laplace transform of my function, and then I'm going to shift the t into t minus a. Okay, so let's apply it here. So this is going to be a unit step of t shifted to t minus 1, inverse Laplace transform of this expression, and whatever the result is a function of t, and then I'm going to shift that to t minus 1. Well, I already know what that result is. I just did it. And so because I just did it, I know exactly what to write down. This is going to be 1 subtract 1/4 subtract 1/4 cosine of 2t, but this entire result is going to get shifted into t minus 1. And so that tells me at the end of the day, I'll have a unit step, t minus 1, that multiplies 1/4, minus 1/4 of cosine 2 into t minus 1. So we found it, and it's time to assemble the whole thing here. So we're going to combine all of our results. Y of t is going to be the following. We had 3 expressions way back when. We had the units, the first term here in blue, which is a half sine of 2t. We'll have a half sine of 2t. That term really came from the initial conditions here. So that term came from the initial conditions, and then we had the other 2 terms that were related to the function on the right-hand side. And those other 2 terms had more or less the same form. So they had 1/4 minus 1/4 cosine of 2t added to the following. Subtracting the same looking expression with a unit step. So effectively, this thing is going to turn off at time 1. Now, you can break down that unit step even further as you need and write this as a piecewise function. So for time between 0 and 1, your solution is just going to be 1/2 sine of 2t plus 1/4 minus 1/4 cosine of 2t, because all that will be left is that first term here. The unit step will turn this one off. And now, after time 1, so when time is greater than or equal to 1, you can go ahead, you can separate everything out. What's going to be left? You'll still have the 1/2 sine of 2t, but these, for instance, the 1/4 terms, these will cancel out, and then you'll have a cosine of 2t subtract the other term. So then you'll have minus 1/4 cos 2t added to 1/4 cos of 2 into t minus 1. So it's the unit step function that allows us to deal with very complicated right-hand sides. Dealing with this kind of right-hand side without the unit step function, the way we would have done in the first part of the course, is a lot more involved. There's a lot more to do in terms of piecewise functions and patching things together. But once you get on board with the unit step concept, it makes very complicated applications possible.